about the homework, any of the homework problems at all? All right, let me ask you this, how many tried it? No problems? None?
You do 714?
714, yeah. I want to do one before I start off into another area. Now, can you get your calculators out? Because the real problem a lot of times is just being unfamiliar with how to do the calculations on your calculator. And it's essential you get it right. Calculate the average power absorbed by the 2 ohm resistor in circuit in figure 713. All right. We'll get them both resistors. This is actually a pretty good problem. This is 714 you asked for, right? Did you say 714? Okay. All right, I'm going to say one thing. We're going to get the power absorbed by both resistors. But before I say anything more, how much average power is going to be absorbed by that capacitor? Anyone? 0. It can't absorb average power. You all follow me on this? I'm just stating it one more time. Now, they are looking for the power, and I'm going to be asking this question on Monday. The power absorbed by that 2 ohm right here, and the power absorbed by that 1 ohm right there. A lot of ways to do this. There's no one best way. How would you try to do it? And what do we ultimately need to get the power based on what I told you? Well, we could get the voltage, but current is obvious, isn't it? Didn't I show you that 1/2 the magnitude of the current squared times the resistive part, if it's a complex impedance, just a real part of the impedance, is the power. How many remember that? Now, you're going to need to know this very well on Monday. So I'll first put it up there that power in general, when we talk about average power, it can be given several ways. One is 1/2 the voltage magnitude, the current magnitude on the element that we're looking for the power absorbed by, times the cosine of the voltage angle minus the current angle is one way. You all remember that? That was one way to get it, and it would always get it the right answer. It's also equal to 1/2 the magnitude of the voltage across the element squared. Well, I'll tell you what, I'm not even going to put that one down there. What I'm going to do is this. It's 1/2 the magnitude of the current. Now it's magnitude, so you have to take the magnitude. There's a real imaginary part. Magnitude of the current squared times the real part of the impedance of the element. And the real part, if it's just a resistor, it's just the value of the resistor. Do you all follow me on that? If you do, raise your hand so I know. Everybody with me on this? Do you have a question? There's some hands didn't go up. Any question about it? When I say real part, some of you may be wondering what I mean, but if I have an impedance equal to like A plus JB, the real part of that impedance Z is just A. Follow me? In other words, it's simply the real value. Does everybody understand that concept? Okay? Now, let's look at the powers associated with these. I'm going to make a statement. Because they give me the current here, if I can find the current here, and I'll just call it I2, and the current here, and I'm just calling that I1 because There's 1 ohm on that side, 2 ohms on that side. That's the only reason I chose that subscript. You all with me? If I find those currents, can I get the power? How many think they can? All right. If you're unsure, please feel confident about this by the time you take the quiz. It should be a no-brainer. I'm trying to encourage you to do this study. So how are you going to get the currents to this 2 ohm? Anybody? Anyone at all? I think current division would be the most straightforward method. You all see that you've got a current going into the parallel combination of 2 impedances. How many see that? I think current division would probably be the easiest. You don't have to do it that way. You can put a ground there, you can find the voltage there, then find the voltage and divide it by the impedances to get the current. But we already have the current. Why not just use that with current division? So I'm going to say that I2 there would be equal to the source current. 4 at an angle is 60 degrees. You're going to see that 60 degrees is worthless. You don't need it. You'll see that in a second. But we'll put it there. Then it's going to be times the opposite impedance. Remember, if you want the current here, it's always opposite impedance over the sum of the two. And the opposite impedance is 1 minus J1 over the sum of the two. 1 minus J1 plus 2 would be 3 minus J1. That would give me a magnitude and angle. You all agree with that? Now to get the current here, well, I could do it the same way. I could take this current and multiply it by the opposite impedance over the sum. You all follow me? That would be one method. Or I could just say, well, it's this current minus I2. You all see that has to be I1. How many see that? All with me on this one? I mean, either way I'll get you. So I'm going to say that I1, pardon me, is just going to be the current 4 at 60 degrees minus the current I2. Now you can do it either way. You can do current division again, it doesn't matter. But the very first thing I need is a magnitude and angle for I2. Can somebody do this? Please, why don't you all do this? Make sure you can do this. One of the hardest things to get people to do is force themselves to use their calculator in class. If you do this, first you'll find out, if you don't know how to do it, it'll be clear and you'll figure it out. But you'll have confidence in yourself. You're not making stupid mistakes, punching in things wrong. I just need a magnitude and an angle from anybody. Anybody at all? Come on, guys. I mean, this should be a fairly quick calculation. There should not be a whole lot of problems here. Can y'all, far back, you guys hear me okay? Anybody have the answer?
I2 is 1.79 at an angle of 33.43.
33.43 degrees. That would be amps. Anybody confirm that? 1. Anybody else? 2, 3. Okay, I'm going to say it's right, unless proven wrong. All right, can you give me I1? And I don't care how you do it. To me, this seems easiest. But learn how to enter a complex number, or really a magnitude and angle, polar number in your calculators, then do the subtraction correctly. This is a lot of times the problem. It's just being unfamiliar with your calculator. Do y'all have your calculators here? Or not? You've got one, I think. Give it a try. And if you don't know how to do it, let me know. I'll get somebody over there if I can to help you. I think most people have TI something or others. Anybody going to the Georgia game? You guys? For real? You're okay, you are. Good luck. Cheney's, all right, you go. We have 2 band members. Are they still here or not? In the marching band, have they split? I don't know. Anyway.
I got the number. Oh, wait. So
I just need I2. Anyone, please? Anyone at all? This may be the foul up on Monday. Yes, sir. 2.5 what? At an angle of what? 78.4? Did you say? 4? Anybody confirm that? Anybody? You got that? Anybody else? 2, 3. Please get your calculators. You got it? Make sure you know how to use your calculators. You won't believe how many people foul these things up. I don't know if you've noticed you've made mistakes in the last quiz based on your, I guess, how you mistakenly used your calculator. I believe there were a fair number, but I can't prove it. Now, do we agree those are the currents? Let's try that. Okay? If they are the currents, then what is the power associated with this 2 ohm or dissipated by this 2 ohm? I'm just calling it P2. Well, it would be 1/2 because these are peak values of current. You all with me? If a cosine waveform was used to describe that current, it would have a peak value of these current magnitudes. Do you all follow me on this? So, as a matter of fact, just so everybody understands this, if I wanted the time domain form of I2, it would be equal to the magnitude, which is 1.79. Then it would be the cosine of omega t. He hasn't specified the frequency, so we'll just leave it as omega t. If we knew omega, we'd put it in there. And then it's going to be plus that angle, so plus 33.43 degrees. And by the way, what's the problem with that 33.43 degrees? Okay. It should be in radians, but it's not. All right, so you'll keep hearing me harp on that, because if it wasn't done in the book that way, I would probably take points off if I ever asked for the time domain form. But because the book is sloppy, I'll let it slide. Okay, anyway, now back to this. It's 1/2 magnitude of that current squared times the resistance. In this case, it's 2 ohms. I'm just putting down the formula direct. You all follow me? The 2's cancel. The 1/2 and 2 cancels. So it's magnitude of I squared. The magnitude of I squared is 1.79 squared. About 1.8. And what is that? Anybody? Can you take 1.79 just squared?
3.2.
3.2 watts. Okay? What about P associated with 1 ohm? That would be 1/2 magnitude of I1 squared times 1, or magnitude of I1 squared over 2, and that would be equal to what? 2.53 squared over 2 watts, and what is that? Say again? 3.2? Is that right, class? 3.2. They're both 3.2 watts. Well, a coincidence probably. I don't know, he might have done it on purpose this way. But you all follow me on this? That's it, really. There's nothing tricky about this. We can do another problem if you like, but what did you, I mean, the one thing I'll tell you that gets people, when they'll see this, people will hesitate, which way do how do I solve this? Should I use Thevenin, nodal, mesh? Y'all follow me? If you know your stuff, you'll take a look at this, and current division seems like the easiest, quickest route to get the answers to me. And it should to you too. Do y'all follow me, class? Just remember what I'm telling you. That's why you have to be familiar with the methods, the other methods, so you can quickly ascertain the values. Now, we could do another problem if you want, but I think all the problems I gave you are the same class. It's circuit analysis to find the current. Isn't that right? You did some of them, right? Did you have any problems with this analysis at all? Did you do current division here? Okay, you don't have to. There's so many different ways to get at the result we want. And that's the nice thing about this type of class, and really probably it's true of mechanical engineering problems and industrial engineering and whatever, civil engineering problems. There's a whole lot of ways to get what you need in terms of the method of solution, and they all ultimately are doing the same thing. But that said, looking down here, I can't really see a problem that's going to cause anybody grief here. They all look like they're basic circuits, and I will not give you any kind of problem at this point with power where there's more than one power supply. I'm not going to give you 2 or 3 power supplies, simply because on a quiz, it would take too much time sometimes to do the complex math if you've got more than one source. So I'm just leveling with you about that. Okay. That said, the next thing I want to talk about is it's the concept of maximizing the power coupled to a load or delivered to a load. And by the way, these have direct applications to all engineering. I mean, if you think about any of the type of problems that you do that are related to, think about, for instance, an internal combustion engine, and it has so much maximum output power and horsepower. You want to couple them, all of that power, ideally to the wheels. But there's all sorts of problems that would cause inefficiency. I think everybody knows if you have a vehicle and you're trying to go up a hill and maximize the amount of power coupled to the actual vehicle, in other words, maximize the power coupled to the vehicle moving up a hill. A low gear probably makes sense, it's a heavy truck, right? Why? Because it would maximize the output power to the back wheels. This is a simple concept. Here we're going to find this, we're going to go through and talk about how that concept would apply if an electric motor was being driven by something. And actually, some of you people will be working probably in the area of hybrid cars and electric vehicles and things of that nature. And this is very much applicable, this concept I'm about to show you. And here's what it amounts to. What they're going to do, any system in the world, any electrical system that's a linear time invariant system, a power supply, a battery's charged, something like this, can always be represented by a single voltage. Here, this would be the Thevenin equivalent or open circuit voltage, but I'm just going to call this some source voltage right here, and it will have some impedance right here. I'm going to go ahead and just put down a real part. I'm assuming the source impedance is RS. Now, this represents whatever the circuit is in terms of its Thevenin equivalent model, but I'm going to leave it in terms of just a real part of resistance, so it'll make understanding this concept easier. Are you all with me? Now I'm putting on a load. This load can represent the actual, well, it would be the electrical resistance of a turning drive shaft, and I'm not going to go there. This has to do with rotating machinery, but nevertheless, it's a load of some sort. And what I want to do is maximize the amount of power here. Now, I'm going to get to this in a second. I know there'll be a current that we'll get to, but I want to find the power at this load, and I want it a maximum. Now, the minute you think of minimum or maximum of anything, if you're engineers, you should be thinking about a derivative of that quantity with respect to the possible variable quantities. Then you set it equal to 0. I think everybody knows that. you're going to do something with a derivative, set it equal to 0, and find out, especially if there's multiple points that have a 0, if that in fact is a maximum or minimum power that's coupled to the load. Does that make sense in terms of the reason? Give me a show of hands if you understand the logic in this. So first I've got to figure out what the power is absorbed by that load for this specific circuit. And I made this real simple. Forget the phasing. So I'm going to say the power at the load, right here, before I do any derivatives, will be equal to 1/2 the magnitude of the current at the load, or really just current, there's only one current here, squared times the resistance of load. I think you can all agree that's it. Now the current through the load, if I made them complex impedances, this would be a little more messy, but the current through the load is just the voltage divided by the sum of those two. Do you agree with that? So this power at the load right here would be equal to 1/2, and then I have source voltage over RL plus RS squared times RL, and that would be the power at the load. Does everybody follow the reason? There's nothing tricky here. I'll take out the things that are constant that can't change. So the power at the load would be equal to Vs squared divided by 2. And then we have this. We have RL over RL plus RS squared. Did y'all give me that? After you just do the math. Now, if we plotted this, if we actually did this, if we plotted the value of resistance at the load versus the power absorbed at the load, I want to just, and this would be the 0 value of resistance. I want to talk to you about that. First, if the resistance is 0, it's a short circuit, right? What's the voltage across the short circuit? 0, right? Matter of fact, what's the resistance of a short circuit? 0. So no matter what the current is, 1/2 I squared could go be very high. Times 0 is still 0, right? You all follow me on that? So when the load itself is a short circuit, there's no power absorbed. Now let's take a look at the other extreme. What happens if I remove the load and I make it an open circuit where the impedance or the resistance goes to infinity? How much current flows? Anyway, it's 0, right? If I have 1/2 0 squared, it's still 0. Do you all follow me? So at the extremes, the power absorbed is always going to be 0. Either when the load is 0 or when it's infinite. You all follow me in terms of the value. Somewhere in the middle, there's going to be an ideal or optimum value that you can, where the resistance of the load will couple the most possible power. And I think you know what I'm going to do. Take a derivative of this with respect to the value of the resistance of the load and set it equal to 0. Does that make sense to everybody? Right? So if I do that, if I take a derivative of the power at the load with respect to the source resistance, well, I can take the Vs squared over 2 here. This isn't going to matter. This is going to be equal to 0 in a second. Then when I take the derivative, now remember, we're taking the derivative of the resistance of the load here. Derivative of RL here is 1, so it's divided by the bottom quantity. Then it's going to be what? RL times the derivative of RL plus RS to the -2, or it's going to be -2 times this over RL plus RS cubed. Now first, take a look at this. Do you all agree with that? Just taking a derivative with respect to RS. Follow me, class? I mean, RL, pardon me. How many see that? Can you all see it in the back? I mean, can you read this? Or not? Can you read it right there? Can you read it, Amanda, or not? Can you guys read it? It's hard to tell with the looks I'm getting. It's like, okay, I'm going to give myself the benefit of the doubt that you can understand that. Now, I'm just going to say it simple. Do you all agree that if we multiply both sides by 2 over Vs squared, we can get rid of that because there's a 0 on this side? So I'm going to. Matter of fact, since this is 0 on this side, I can get rid of this, right? And since that's a minus sign right there, I can just equate these two terms. So I can have 1 over RL plus RS squared is equal to 2 over 2RL over RL plus RS cubed. Now, I think everybody can see that, right? Can you all follow me in this class? Now, multiply everything by RL plus RS cubed, and this goes away. And you're left with what? RL plus RS. You can just see I'm manipulating to get one statement. It's easy to understand. Y'all with me, class? And then subtract 2RL from both sides. So I have RL minus RS equals 0. And that means RL equals RS is the value that will maximize the power couple. Now that's always true if you have a source resistance and a source load, or a load resistance. If you have a complex source impedance and a complex load impedance, this is the case. Write this one down. So if this is no longer the case, but if I want to maximize the power couple, this is still going to be V source here. And I'm going to change 2 things over here to make it clear. Now, instead of having just a real part, I'm going to have some source impedance, and Z source is going to be equal to some source resistance plus J, and I'll call it X of S. So it's going to be a complex source impedance. Do y'all follow me? You will find out if this load impedance, and I'll call it Z load, when ZL is equal to, same magnitude here, only minus JXS right here. So if that's a positive J5 ohms, this will be a minus J5 ohms. That's called the conjugate of the source impedance. The symbol for this would be ZS and an asterisk. It's called conjugation. How many remember conjugation from your math courses? Right? You all had it. The only thing conjugation is if you have A is equal to, and I'll give you a specific example, 5 plus J10, then A conjugate is simply 5 minus J10. It's that simple. You remember this conjugation? It's a very simple idea. And that will, and you can prove it to yourself, but one thing you can probably see, if I looked at the value of current here, as in the other case, it would be Vs divided by Rs plus JXS plus Rs minus JXS, and the imaginary components cancel. And you're left with just 2Rs, just like you were with the prior one when RL was set equal to Rs to maximize power. Do y'all follow me? That will maximize power. If the source, load impedance is the conjugate of the source impedance. It's not a hard concept. He gives some problems about this. I don't spend a lot of time here, But the real trick is you have to get the Thevenin equivalent of the system to do this kind of thing. So in his problem statement, well, one of the problems he'll show you like this. In 723, and I want you to just listen to me about this because this is an important concept. And in this day and age, with so many electromechanical systems happening, it's probably very important, for the enemies especially, to understand this. So this is 723, and I'm going to do it. I think I can do it right here. I'm just curious about one thing. I think I know the answer to this. What is the line on our game against Georgia?
22.5.
For Georgia? Oh boy. Wow. Is Alabama number one or not?
Yes.
All right. Now this problem is going to really give you a great example of how to apply that theorem to a real problem. Here, they want the value of ZL right here that'll maximize the power to ZL. Do you all follow me? That's the idea. They want the value of ZL that'll maximize the amount of power absorbed by ZL. Do you all follow me? So the first thing you have to do is create a Thevenin equivalent circuit of everything on this side. So I'm going to do this, make sure you see what I'm doing. Here's the load right here. I'll just call this, here's where my load is, right? So the first step with Thevenin is always remove the load. So my load is ZL, is removed. And I'm going to do it right like this. Then the next step is we have to find the open circuit, and that's oftentimes in the book and other places called V Thevenin. It's just the value that would occur if you took the load off. The term load is used universally to anything that's going to require current, power, or voltage. Once I do that, how do I get this voltage? I'm going to just ask yourself this. If this was a quiz, how would you get it? Now, I'm going to ask an obvious question. How much current flows through that capacitor with the load removed? How many see it's zero? Nothing can flow, right? There's no way for the circuit to be complete. If nothing flows through here, what would the voltage be across that? Zero. Do you all follow me on that? So really when I want this voltage, if I start at the negative terminal, it's just going to be what? The voltage across this resistor. Do you agree with that? What is the voltage across? Please look and just watch this. Make sure you understand this point, because it is this simple. What is the voltage across this resistor? Do you agree all the current flows through? All of it, right? What's this voltage going to be? 1 times 6, or 6 volts at 0 degrees. Do you agree with that? How many do? I'm trying to make it clear. It's as obvious as it can be, but you have to convince yourself. All right, so what is this voltage? I always start at the negative terminal and increase is 6, right? It's just 6 volts. How many see this? Can you all see it? Down here, guys? All right. That's the voltage. Now, the next thing is, now I have the second thing, which is VOC here is 6 volts, just 6 volts. Finally, the third thing is I need Z Thevenin, or I need the Thevenin equivalent impedance looking back, right? You agree with this? What do we do with a current source? There's a live current source there. What do we do with a current source if we want the Thevenin equivalent? Well, we turn them off. When you turn a current source off, the current goes to 0, or it becomes an open circuit. Do you all follow me, class, on that one? How many do? So you might as well just erase it. Now, just by looking, can you see what the Thevenin equivalent impedance is? How many can? I'm not going to ask you if you don't want to talk to me, but it's just going to be what? 6 minus J1. That's it. So this is simply 6 minus J1 ohms. So now I build the circuit. Here's my open circuit, the open circuit here, which is...
Would it be 1 minus J1 since the resistance?
Oh, I'm sorry, 1, my bad. Thank you. You're absolutely right, I'm so sorry. It is 1 ohm, my bad. It's just the resistance plus the impedance of that, so it's going to be, now I'm going to go ahead and put it in here, so it's going to be 1 minus J1 ohms here. And now I want ZL, right? So what is this value of ZL going to be, people? To maximize power to the load. I've got it there as a blank. People? It would be the conjugate of this. Do you all follow me, classes? You don't want to talk to me today. I don't blame you. Say it's Friday. Okay. Well, maybe Wednesday you'll talk. Yeah. All right. So it'd be what? 1 plus J1 ohms. How many see that? It's the conjugate. Correct, class? Now the way you know is the imaginary component will cancel if you add them up in series. It has to. That's just the way it is. Do y'all follow me? And that, in fact, would maximize the amount of power coupled to the load. Got one last question. All right. So this is the value of the load impedance that would maximize the power. What is the power that would be absorbed by that impedance? Let me erase this and just show you what it is. So the actual load looks like 1 ohm and plus J1 ohm, right? We want the power absorbed by that. Listen to me. How much power is going to be absorbed by that inductor?
0.
Average power is 0. All the power would be absorbed here, correct? How would you get it? It'd be nice to have the current. Do you agree? What would the current be here? Now, some of you can take one look and see it. Well, I got an open circuit voltage of 6 volts, right? And what's the net impedance? 1 and 1 is 2, isn't it? Can you all see that? The real parts survive, the imaginary parts cancel. You all see that, class? So that means I have 2 ohms, or this is going to be 6 over 2, or 3 amps. How much power is absorbed by that load? Only the resistor would be absorbing power. Do you agree with that? It would be 1/2 times 3 squared, or 9 divided by 2, or 4.5 watts. How many see that? And you will find exactly 4.5 watts will be dissipated here and this one off. Exactly the same. Go with me? Which means a total of 9 watts was supplied by the source. That's all I'm trying to point out is the obvious. Everybody with me on this? That kind of a problem is a gift. The only thing you need to do is calculate the Thevenin equivalent circuit, take the Thevenin impedance and conjugate it for the load, and then calculate whatever, all right? And it's really that simple. Are we good on this one? I'll give you problems on this. This is something you work and just reinforce that ideas. Yes, sir. All right, can somebody tell him why this became positive J1? Anybody? In your own words. Anyone? I know it's Friday.
Conjugate of.
First, you're absolutely right. You see that this is the source impedance right here. Can you see that back there? 1 minus J1. The conjugate of that would be the load impedance for maximizing power. The conjugate takes the minus J1, makes it a plus J1. There are no dumb questions here. I mean, to be frank about it, with my handwriting, sometimes I worry that you don't understand what I'm writing, but I'm trying. Are we good with this? Yes, sir. Sir, hold it. Speak up. Power supplied would be the power dissipated by the 1 ohm resistor here and the 1 ohm here, right? Well, there was 4.5 watts in the 1 ohm at the load. There's exactly 4.5 watts in the 1 ohm in the source. The sum is 9. With me, everybody? Okay. I mean, ask questions if you don't see something. There's no dumb questions. Okay.
Oh, I got one. So the conjugate there, or the 1 minus J1, is the Thevenin, right?
It's equivalent source impedance. It's the Thevenin impedance of the circuit. When we got the we had to get Z Thevenin and V open circuit or V Thevenin. So all those things, you have to get the Thevenin equivalent circuit to do these problems. That's the idea. Might want to do one more just to clarify. I think you guys will get this. I'm trying to find one that's a little more difficult. All right, we could look at 7.25. They're all the same type of problem. All right, so they're going to want to know the value of ZL that'll maximize power to the load. And I'm going to ask for the value of the power to the load. So how do you do that problem? Just go through it step by step. What's the first thing you do if you're going to do a Thevenin equivalent circuit? Well, here's the load. Right? We don't know what it is yet, but you remove it. So ZL is the load. Then I remove it. And here's the value of V open circuit or V Thevenin. Do you all agree with that? How do you get that? How would you get that? Oh man, I mean, there's going to be a couple different ways. They're all equivalent. Well, I have 12 volts, right? I have 1 ohm and J1. Does everybody agree the voltage right there across that J1 is the voltage VOC? How many see that? Has to be correct. Correct, class? How would you get that? Voltage division looks good to me. You agree with that, class? Yeah. So V open circuit here would be equal to 12 Then it's times J1 over 1 plus J1. And what is that going to be? So that's 12 at an angle of 90 degrees over square root of 2 at an angle of 45 degrees. So that's 12 over the square root of 2. And the angle here would be 45 degrees volts. What's 12 over square root of 2?
8.49.
Yeah, sounds right. All right. The next thing is what do we need now? Z Thevenin, which will be my equivalent source. So what is that? What do we do next, class? What do we have to do with this 12-volt source? You turn it off, make it a short, right? It's a voltage source, becomes a short circuit. So if it's a short circuit, it looks like this. You agree? How many see that J1 and J1 are in parallel? Can you all see that back there? Over here, guys? They're in parallel, right? So that means Z Thevenin, I'll just put J1 in parallel with 1. Or here, it's what? J1 over 1 plus J. And that's what? 1 at an angle of 90 degrees over square root of 2 at an angle of 45. So it's 1 over the square root of 2 at an angle of 45 degrees. And what is that? Simply 1 over square root of 2. And that's going to be equal to, and then you're going to have 1 over square root. So it's really going to be 1/2 plus J1/2, isn't it, class? Isn't that right? Just, anybody want to confirm that or deny that? I think that's right. And that would be ohm. So now we build the circuit, and we have a voltage here. This is my open circuit voltage here of, what is it? 8.49 at 45. My impedance is going to be 1/2 plus J1/2. And now, what is the load impedance going to have to be because of that?
1/2 minus.
Exactly, 1/2 minus J1/2. Follow me? That will maximize power. What is the power that will be absorbed by the load, class? Let's try this. This is the load. What's the current going to be flowing here? It would be this divided by what? 1. You all see that? 1/2 and 1/2 is 1. The minus J1/2 and plus J1/2 cancel. So it's just going to be equal to 8.49 amps, and I don't really care about the angle because that means what? The power absorbed is really the power absorbed by the 1/2 ohm, and that would be 1/2 that current, which would be 8.49 squared magnitude of current times the resistance 1/2. So it's really, I need this one value. And square it divided by 4. What do we get for that, class? Anyone? We're a lively bunch today. I don't know. Is it a test or something?
Fluids exam.
What? What exam?
Fluids.
Fluids? How many had a fluids exam? My sympathies. All right, what's 8.49 squared over 4? Was that fluids 1? Don't you have fluids 1 and 2? Just 1? Thermo 1 and 2. They're so much fun. Steam tables is the only thing I really didn't like. What's the value for that? Anyone? 8.9? All right, there you have it. See you Monday.